Good morning, everyone. I'm Justin from the AI Frameworks team at Microsoft. We have built something that makes working with ONNX graphs drastically easier and more pleasant, and I'm excited to share with you all today. In today's talk, I'll introduce two projects, the ONNX IR and the ONNX Rewriter. This talk showcased the work done by Bowen, Shubham, Aaron, Wei Sheng, me, Manav, Xavier, Rama, and Ditai. I'll first talk about our motivations for building the ONNX IR and highlight the two areas where the IR can be very useful, graph construction and transformation. I'll then share resources on how you can get started today with the IR and the rewriter. When I say ONNX IR, you may be wondering, isn't ONNX already an IR for machine learning models? What does it mean to build an IR for ONNX? Let me clarify what I mean. We have built an in-memory representation for ONNX in pure Python that allows you to construct, manipulate, and analyze ONNX graphs independent of the protobuf structure. Now, we left ONNX as a standard and a file format for representing ML models. However, when we want to construct and manipulate these models, we often find ourselves having to interact directly with the protobuf data structure. As protobuf is designed to be a serialization format and is not efficient or robust for manipulation, transforming ONNX graphs tend to be inconvenient and complex when done directly on protobuf. To see how ONNX IR can help with constructing and manipulating models, I would like to invite you to go on a journey to see how one ONNX model is produced, starting from a framework, in this case, PyTorch. A common way of obtaining an ONNX model from PyTorch is using the Torch ONNX exporter to capture and convert the graph. On the slide shows a very simple model. This is a PyTorch model with a single Gaussian error linear unit function, or GLU. The function is exported as a composition of 5 ONNX operators, which we see on the right. As we build a PyTorch to ONNX exporter, leveraging the Dynamo technology in PyTorch, we found that the exporter works fine until we start to export models with gigabytes of parameters. One complaint we hear from users is that it takes too much memory to export the models. It boils down to how we handle large tensors when constructing ONNX graphs. During the export process, there's a step where we use the load external tensor for model function to load all tensors back as protobuf in order to further process the graph. Sure enough, when the weights are large, machines run out of memory, and in this case, it more than doubles the memory required. If not careful, protobuf equals high memory usage when you work with large tensors. Instead of requiring the tensor data to be serialized, the ONNX IR allows developers to create a compatible tensor interface to share tensors coming from machine learning frameworks and avoid copying data. And so we implemented the interface for Torch tensors. So now we can build our graph with minimum memory usage and run all sorts of transforms and analyses on the graph without duplicating a single tensor. The toBytes method shown here tells the serializer how to turn the tensor into a byte sequence only when it's time to save the weights to disk, so you won't see a peak in memory usage. This is especially relevant with the large language models nowadays that have billions and even trillions of parameters. Not having to copy tensor data means you can construct and transform any graph confidently without getting out of memory errors. Now, in addition to handling tensors correctly by default, the ONNX IR presents a set of Pythonic APIs that closely mirrors the ONNX Helper APIs that you're familiar with, but with a twist to make it more ergonomic and intuitive. To start, accessing elements in the graph is straightforward. Values are now objects in the graph instead of strings, as you would see in protobuf, so you can modify properties like shape and type without having to maintain auxiliary data structures for value info proto lookup, for example. The produce and uses method, as well as built-in iterators, make graph traversal easy. So you can now kind of trace the graph with these methods with these methods by looking the graph like a tree. We make choices in the IR to keep the APIs intuitive and minimal. What that gives you is a sense of confidence and fluidity when working with ONNX graphs. So this is ONNX IR for graph construction. ONNX IR is being used or will be used in our improved version of the PyTorch to ONNX exporter in ONNX script, and is perfect for your next project. Next time when you find yourself having to work with protobuf, I encourage you to try doing it via ONNX IR. Now, ONNX IR provides a Pythonic API and is efficient for constructing graphs, but it really shines when it comes to manipulating and optimizing ONNX models. Now, let's bring back the GLU model we just exported. After obtaining an ONNX model, the next step is usually sending it through a series of graph transformation passes to clean up, optimize, or quantize the model. For different backends, there's also graph fusion that can be done. Our ONNX runtime backend has a single kernel for GLU, so it would be good if we can replace the subgraph with the GLU operator or perform a fusion on the 5 operators on the left. It would be great if we have tools to do this, and they do exist. But before the IR, if you were to build a graph optimization tool for ONNX, you have roughly 2 choices. First, you can load model as protobuf, as a protobuf object, and directly manipulate the data structure. But the protobuf data structure exhibits quadratic behavior when you insert elements, and there's a lot of bookkeeping you need to do to maintain coherency of the graph. The next option is that you can build your own APIs for representing and manipulating the graph. This requires a lot of effort and thoughtfulness, so they are often designed with a subset of ONNX spec in mind. They tend not to be easily reusable, and you would have to rebuild something similar again for a different project. We designed the IR to provide low-level methods for manipulating ONNX graphs. Iteration of nodes in the graph is safe, however you mutate the topology. You can feel extra confident about your changes by implementing invariants on the graph, and we keep performance in mind, so most operations on the graph is O of 1. Now, the act of identifying and replacing subgraphs is powerful, because not only it is great for fusion, it enables developers to create all sorts of optimization on graphs, just with this simple idea. To make it even easier, we have built the ONNX rewriter for you using the IR. The ONNX rewriter provides high-level APIs for graph replacement. All you need is to provide a target pattern and a pattern to replace it with. Bring back the ReLU model again we can create a target pattern as a function in the ONNX script syntax, the same natural way as you would express the logic if you were creating a PyTorch model, and create a replacement pattern with a single GLU operator. Then we create a rewrite rule and apply that to the rewriter, which will produce a fuse graph that's on the right. The rewriter also accepts a condition to determine matches based on additional checks on the match patterns, and it allows you to generate replacement pattern based on the match subgraphs. So you can generate context-dependent replacement as you wish. We have used the rewriter to build a set of optimization rules that is currently serving the Torch ONNX exporter to ensure that the exported graph is optimal. So now you can transform and optimize ONNX graphs simply and robustly using the ONNX IR and the rewriter. With just a few lines of code, you're empowered to create your own optimizations that target your specific needs using the ONNX rewriter. You can also create lower-level passes that gives you full control over the graph with ONNX IR. With ONNX IR mutation APIs, and the PaaS infrastructure that it provides. We're excited for you to get started today. Both the ONNX IR and the rewriter are currently offered as part of the ONNX script package, which you can install through pip. To get started with the IR, simply load your model using ir.fromProto method and start exploring the object. You can go to aka.ms/onnx-ir for more information. To get started with the rewriter, you can go to aka.ms ONNX rewriter tutorial and follow the tutorial to experience the rewriter. As always, we welcome you to create issues on the ONNX script GitHub repository, and please do reach out to us on Slack. Thank you. And I'm open for questions.
What's stopping ONNX script and ONNX IR from being mainlined into just the ONNX repository?
I think we're exploring this option. We're still in early stages of developing the technology. So we think having it validated and ensuring that it's doing what we want them to do, both in actual projects like the exporter, as well as the rewriter and everything that we're building is important. And I think we're all for contributing it to ONNX, and that also depends on community feedback and where the community want the library to go.
Thanks.
Hey, Justin. So
yes.
This is really good. I think this has got a lot of value because I see a lot of frameworks developing their own graph IR for manipulating ONNX graphs, translating protobuf into their own IR. So this is really useful. The question is very specific. Do you envision having C++ APIs for ONNX IR? And I'll tell you why I'm asking, because you were talking about subgraph substitution. A lot of runtimes actually like to do that on the fly at the beginning when they're loading the model. And a lot of them cannot have Python in their environment. So it might be useful to have something in native.
Yeah, that's a great question. Thank you. So the question is, do we want to have a C++ implementation? So there are a few things we want to validate. So the value in ONNX IR, some of the values that we provide in ONNX IR include how we model the data structure so that it's really designed for the ease of manipulation, as well as the API we provide that is very thoughtfully designed so that is a very limited set of APIs and yet still very powerful. So we want to validate that, and Python allows us to iterate very quickly and build out those validation very quickly to show its value. Now, there are two ways for us to expose a C++ API and kind of integrate this whole idea and provide that in Python as well. One is that we can implement something similar in C++ and kind of use a bind or some binding method and expose that in Python. Or we can implement, kind of mirror the APIs and the underlying idea in C++ and maintain the Python implementation there. I think at this point, the way I see it is that it's important for the implementation to be complete in Python, because that gives developer the full transparency of what that is doing. And so, if you are developing in Python, you have the full transparency and extensibility that Python provides. So to answer your question, we want to make sure that it's doing the way we want it to function and provide the value that we want it to provide. And then we'll explore C++ implementation. Obviously, we welcome contribution and ideas. So if anyone here decides that a C++ implementation is great and they want to contribute, we welcome those conversations. I think Rama was trying to say something.
Yeah, I guess with respect to the rewriter specifically, I guess one of the possibilities to actually take the rewrite rules as specified here, but compile them and emit C++ code actually that does the same transformation. I mean, it's not done today, but that's a possibility. Yes. Thanks.
Yeah, quick question about, so is there any coupling between the IR and the runtime? So if I were to create an IR, is there some sort of validation that I could know ahead of time if it's going to actually run? And I guess coupled to that is, can you write custom ops in this IR? And how would that interface with runtime?
Yeah, that's a great question. So the first question, is it coupled with any IRs? Not at this point. The ONNX IR right now is IR agnostic, so it's only for representing the graph, transforming the graph without any assumptions on any IRs. But if that's something that people can find useful, there are options to explore there, so that validation and just experiments can be fast. Now, the second question is about custom ops, which brings us to this slide, which I haven't presented. Yes, it has full support for custom ops. In fact, it treats the ONNX native ops as though they were custom ops, and there's no difference if you were to create ONNX native ops or if you were to create custom ops. The ONNX IR is able to represent the full set of valid ONNX models that ONNX protobuf can represent, and a subset of invalid ONNX models, and therefore you can load them into the IR and maybe do fixing and analysis on those models. Now, we cannot represent the full protobuf because it's too freeform, and sometimes it just doesn't make sense for it to exist in that form. And additionally, we also support a subset of models that ONNX protobuf at its current state does not express, and some examples include having a mix of offset versions in a graph. And that allows us to kind of incrementally do version conversion, for example. And you can embed a lot of metadata in any of the entities. So if you're writing passes, you can record, for example, from a previous talk, we talk about traceability and figuring out how the graph has changed during different passes. Those are the metadata that you can embed and carry forward with the ONNX IR data structure, and you can use that to kind of enhance the tools you built, and only when you serialize do we go from there to protobuf. So if that answers the question.
Oh, definitely. Yeah, thank you.